Now, this is an interesting problem because we have a time shift that happens in here for one of these vehicles. So we got to figure out how to handle that. All right. So we're going to draw a diagram. And how big's my diagram going to be, Andrew?
It's pretty big.
It's going to be pretty big. Full width of my paper here. We're going to start each one of these cars over here in the starting line.
Here we go.
All right. We've got Stan and we've got Kathy. Okay. So Stan leaves. And Stan leaves. He's got an acceleration of 3.8 meters per second squared. What's his initial velocity? 0 meters per second. All right. Initial position is 0 meters, right? And then we've got Kathy. All right. Kathy starts 1 second later. All right. And she's got similar numbers. She's got initial velocity of 0, and she's got an acceleration that's higher. Let's do a little table of initial values for these. And he starts at t0 equals 0 seconds. All right. Kathy, similar, right? What's different? That's the difference. Okay. So later on, Stan's going to be over here, time 1. All right. At that same time 1, we want to figure out when Kathy catches up. All right. So over here, we need to figure out the time. So we want to find what this position is. Anything else?
Speed.
And we want to find the speed. So we want to find the velocity of Stan, Vx1 for Stan, and Kathy. These two numbers are going to be the same. Are the velocities going to be the same? I would expect that, she's going to be flying by him, so she's going to be going faster, right? Because she's a better driver than she is. She isn't cheap. All right. So let's work out some equations for Stan. We'll put Kathy down below here. I'm going to write the same equations. So for Stan, we got to put in some numbers here, right? So we know his AX is 3.8. We'll substitute it for that, right? We know his initial velocity is 0. That's nice. That's going to be gone. And his initial position is going to be 0. All right? So same thing here. His initial velocity is going to be 0. Okay? So let's go ahead and write up Stan's equations then. So there's Stan's equations. Easy enough. Now, here's a trick. I want Kathy's equations to use the same time that Stan's is using. How do I do that? All right, we got to change her t. And by the way, this is in math. We've done this before, all right? You have f of x, right? And we do a substitution. If you want to take a graph and we want to shift it in time, right or left, what do? What's a right or left shift look like? Let's say we want to shift it to the right 3 units. We do f of x, what? Minus 3. All right? Remember how we did these translations in math? Same thing's going to happen here, right? We're shifting her car in time. So let's just pretend we're not shifting in time. Then let's revisit and shift it, all right? So let's just plug her numbers in. And she's going to start out at a 0 velocity. And she's going to start out at a 0 position, all right? And her acceleration is going to be 5.35, is it? So let's look at this, and then let's figure out how to put the time shift in. But if we started this at time 0, at time 1, she'd actually be moving, and she'd actually have moved, right? She doesn't know. We've got to delay this for a second. At time 1 second, it should be at 0, all right? Not at time 0. At time 0, Stan's at 0. At time 1, Sam's moved along a little bit. Stan has moved along a little bit. And at time 1, Kathy's still sitting there. So if I plug a 1 into here, Kathy should still be sticking on the starting line, all right? But if I plug the 1 in this equation right now for both of these things, I'd get 2.675 for the position, and I get 5.35 for the velocity. They're supposed to be 0 still. What do you plug in here? Think about this. T minus 1, all right? So we're going to have x equals 2.675 T minus 1 squared and we have Vx1 equals 5.35 t minus 1 here. All right. If we do that, everything works out perfectly. We're using the same time for both problems, and we want to have the same time for both problems because that gives us our system of equations to work with. If we didn't have the same time frames, it wouldn't be a system of equations. We couldn't link these two cars together mathematically. All right. So now, if we start out at time 1 here, what happens? 1 minus 1 is 0. We start at 0. 1 minus 1 is 0. We start at 0 velocity. Now these equations are synced in time. All right. Those are the equations for Stan's position and velocity versus time, and these are the equations for Kathy's position, velocity versus time. What do we do to solve this? Well, what were we asked to solve for? Find t when what is true? Find the time when Kathy's position equals Sam's position. Here's Kathy's position. Here's Sam's position. So how am I going to figure out when they're equal? Yeah, when they're equal, these two numbers will be the same, so I get to set these two equations equal to each other. Right? So we're going to have when x1 for Stan equals x1 for Kathy, is what they told us. All right? That's the condition they gave us, so we're going to do that. Well, x1 for Sam is just 1.9 t squared, and for Kathy, it's 2.675 t minus 1 squared. All right? How do you solve that? Give me two ways to solve this. And by multiplying this out, what do I have to do for that t minus 1 squared? You got to FOIL that. Very good. So I'd have to FOIL this, and I'd have to distribute the 2.675 t squared in, and over here I'd have the 1.9 t squared in that I had to do. Could somebody give me an alternative way to solve this? Does anybody think I can solve this without doing any calculations whatsoever? I'm going to graph it. I'm going to do a graphing solution on this one. Now, I'm a big fan of using algebra, so I'd expect on a quiz or test use algebra. But if you're short for time, I do a graphing solution. Feel free. I'll give you at least partial credit, but you got to show me what you do. You got to tell me what you do. All right. So let's actually graph this. Let's find a graphing solution. I'm going to graph the left side and the right side, and where they cross is where they're equal, where the times are equal, and we'll see what happens. All right. Let me see if I can flip this over here.